This video is part of CAE Associates ANSYS e-learning series. CAE Associates is an engineering consulting firm in Middlebury, Connecticut, specializing in finite element analysis and computational fluid dynamics. We have been an ANSYS channel partner since 1985 and have developed our ANSYS e-learning series to help you maximize your software investment. Please visit our website, which includes an extensive resource library with over 250 items and counting in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of performing engineering analysis. CAE Associates also offers an extensive schedule of ANSYS courses taught at our Middlebury office. If you need help deciding on the best courses to take for your application, visit our CAE University page. The complete library of e-learning recordings is available for viewing in our resource library and also on our YouTube channel at youtube.com/CAEAI.
I'm going to talk about how to analyze pressure drop in valve flows using ANSYS CFD. Okay, so in today's agenda is about trying to solve a valve flow problem. So I'm going to give you an overview of a typical valve flow problem. And following that, we're going to set up the CFD analysis for that. We're looking into the details of the geometry requirements, the meshing requirements, and then dig deeper into the solver settings. And for this, I'm going to use ANSYS CFX. And at the end of, after you're done with the solution, we'll look at the data and post-process it using CFD Post. Here I'm going to look at both quantitative and qualitative data. All right, so what you're looking over here is a typical ball valve. So you can see the geometry of the valve. This is in the center. It's connected to two pipes. So I'm going to consider the whole setup for the simulation. The reason for that is that the pipe extension helped me to set up a well-posed boundary condition. I can make sure that my incoming flow is fully developed and my the exit is far away so that it doesn't affect the flow within the valve. And we'll just discuss briefly about that later on. So if you look at the valve geometry, it's pretty straightforward. As you can see, as the ball valve will turn, it can lead to a partially closed condition or a fully closed condition. And depending on how close it is, it can regulate the flow through the valve. Now, this is a typical problem where you will see a pressure drop. In an ideal case scenario, what you will find is that you would expect that the pressure is completely recovered at the end, at the exit of the valve, but that's not true. In reality, we always have some pressure loss in this kind of systems. Now, the reason pressure loss occurs is due to some resistance to the flow. This could be because of friction, viscosity, roughness, or due to geometry changes such as sudden expansion or contraction. So we're going to examine two different scenarios. One is a fully open case. That would be the case where the valve is going to allow all the flow through it. And another is I'm going to consider a 15-degree closure where it's a partially closed condition. And with the closing of the valve, you expect that there is an increase in the losses due to that. Before we proceed, we are going to look at one more characteristic of the flow, which is called the Reynolds number. Now, as you know, the Reynolds number is essentially the ratio of the inertial forces to the viscous forces. It's essentially a function of the fluid density, velocity, some characteristic length, such as the diameter, and the viscosity. So if the reason you consider the Reynolds number is if the Reynolds number is sufficiently high enough, the flow can turn turbulent. And typically for a pipe flow, it could be the critical Reynolds number is around 2300. So in that case, you need to make sure that your model also considers turbulence when it's solving for the problem. Okay, a couple of prerequisites before we proceed. I'm assuming that all of you are familiar with Design Modeler and meshing tools. If you are not, then I would recommend that you take a look at some of our previous e-learning sessions. This is available at the resource library at our website and also on our YouTube channel. Okay, so first things first, let's look at how the geometry will look like. We can extract, based on the geometry, we can extract the fluid domain, and it will give you essentially a flow-through domain like this. Now, the second thing to do is to defeature all the small features. I removed some of the blends, which I don't think is going to be affecting the flow physics. I removed those, and then I'm going to modify the flow domain a little bit further in order to make sure that it's compatible with the meshing strategy I'm going to develop. So one thing to look over here, this is a flow-through domain. It has two pipes which are essentially cylindrical, and here what I'm going to do is decompose into three parts for two pipes and the valve. And I'm going to talk more in detail what I had done so in upcoming slides. And when you look at the fully open case, the center tube is essentially parallel to the pipes, while when I have 15-degree closure, you can see that the tube is turned slightly, and so there is a change in the cross-sectional area over here. And these, how to extract a flow-through domain and how to decompose the geometry have been covered in a couple of our e-learning sessions. One more thing to consider before you jump into meshing is to look at the boundary conditions and make sure you have identified all the wall regions. So I have an inflow and an outflow, and the rest of the regions is walls. So wherever walls are present, I need to make sure that there is a corresponding inflation there in order to capture the boundary there. So based on this knowledge, I'm going to devise a meshing strategy. So I'm going to use inflation on the walls, like I mentioned before, to make sure that I capture the boundary layer. And then I'm going to use sweep mesh wherever possible to make sure that not only my mesh has a reduced count, it also gives me a mesh which is aligned to the flow, giving me prism or hex elements, and it gives me a good quality mesh at the end of it. So I'm going to use a sweep mesh for the pipes, and in the center I'm going to use a path conforming mesh, which is going to generate tet meshes. So I can use also element or phase sizing in order to refine the regions on the body. And once I'm done with that, this is how my mesh will look like. You can see that I have inflation layers on the walls, and I have tet mesh in the center, and prism elements and hex elements in the sweep section, section, sorry. So once you're done with that, you need to make sure that your mesh statistics are within permissible limits. You're looking at features such as orthogonality, skewness. This will make sure that I don't run into problems when I'm running the solver. Again, how to generate these meshes and generate inflation layers have been covered in a couple of our e-learning sessions. Once I'm done generating the mesh, I'll link it to the ANSYS CFD solver, and I open the CFX pre, where I can choose the different kind of conditions I need to set for my solver. I can choose analysis type, the specifications for the flow domain, the different type of boundary conditions, and also the solver settings. And we're going to look into this in detail by taking a demo and working with that. So I'm going to open my project page over here. So you can see that I have different component systems. I'm going to basically choose the first set of conditions. I'm going to work with the fully open case. So I have the geometry which I've defeatured, generated the mesh, and then I linked it to a CFX component system. And then when I open the setup, it opens the CFX pre, and this is how it will look like. So one thing to note over here, when I decompose my geometry, it gave me three bodies by I meshed it as a single part. So when it is brought into CFX pre, it is seen as a flow-through mesh. What I mean by that is that although I have three principal 3D regions, if you look at the connectivity, it shows me one-to-one regions, which basically means it's conformally mapped, and the CFX sees it as a single block of mesh. So once you're done with once you're brought in the mesh, second thing to do is look at the analysis type. You can choose it to be a steady state or transient case. Here, the solution, we are expecting it to reach a steady state, so I'm not going to change that, choose a default value for that. Second thing to do is I'm going to insert a flow domain. So I'm going to call it domain and call name flow domain. Once I'm done with that, I need to choose the location for that, which I can choose using either my cursor, or I can choose the whole assembly and specify the location to corresponding to that. Second thing is you choose a domain type. In this case, a fluid domain. The coordinate system is not changed. Once you define the location and the type, next thing to do is define the type of fluid you're going to use. And this is selected through the material library. The default over here is air, but we are going to use water, which is an incompressible fluid. So we are going to use a constant, we're going to use the material definition for water which has constant property, and I'm going to select that. It's a type of a continuous fluid. Once I specify that, I set a couple of other conditions such as the buoyancy and the reference pressure. Now, setting the reference pressure, you have to be careful in order to make sure that whenever you set a reference pressure, you have to remember that CFX is working with the relative pressure. So when you look at the absolute pressure, it's basically the sum of these two. So if you set a boundary condition somewhere else, you are setting the relative pressure. It has to correspond to the reference pressure. For example, at the exit, if my flow is at 1 atmosphere, I set a relative pressure of 0, which we are going to do for this case. Then I can choose whether or not the flow is buoyant, so I'm going to neglect the gravity effects over here. Once I'm done with that, I move to the Fluid Models tab, where I can set the heat transfer and the turbulence characteristic of the flow. In this case, I have no heat transfers. I'm just going to set it to none. And as I mentioned before, turbulence is present in this case, so I'm going to choose an appropriate turbulence model. In general, this flow will, we expect to see some kind of separation as it exits the valve region. And in general, it's known that the KF model does not work very well with adverse pressure gradient or separated flow cases. In this case, it's better to use K omega model, which works very well. So I'm going to choose that, and I'm going to set OK. Next thing to do is set the boundary conditions. So I'm going to insert a boundary in the flow domain, call it inlet. Notice that the location was automatically selected. This is because I have a name selection called inlet already over here. Name selections are interlinked, so any name selection in design model is carried forward to the meshing to the solver if you want. So I would recommend that if you can, try to have as many name selection as possible so that you can group all these individual phases as boundaries. So I can either use the cursor or use the selection dialog box to specify it. Then I can specify the boundary details such as the mass and the momentum, which could be the speed, the mass flow rate, or the pressure. And I'm going to set the speed to be 1.5 meters per second. I'm going to set apply. Next thing to do, I need to insert an outlet condition. Again, I have a name selection called outlet, and here I'm going to specify the boundary details of static pressure, which I could also specify as mass flow rate or the speed. And I'm going to say relative pressure of 0. That means it's an absolute pressure of 1 atmosphere. Last thing to do is set the condition for the wall. So I call it wall, and I choose two locations for the pipe and the valve separately. And here in the boundary details, I set it to be no-slip wall. Notice I can also set the wall roughness if I want to. I'm going to choose this to be a smooth wall for this case. Okay, once you're done setting up the flow analysis, you go to the solver and you can set the solver control settings. You can go and choose the type of, the order of the scheme you want to select for these cases. For example, for the adversarial scheme, I can choose a higher risk scheme or a lower risk scheme. In general, I would recommend that you always work with a higher risk scheme because it will ensure your results are more accurate. In certain cases, it might not be possible to do so, and in that case, it's better to have an initial condition using a first-order scheme, such as an upwind scheme, and use that initial condition for the next set of calculations where you use a higher-order scheme. Similarly, you can set the convergence control criteria. I set usually the maximum number of iterations to be a little bit higher to make sure that my solution is converged. And then you can choose the fluid time scale, which could be auto time scale calculated by the solver, or local time scale, or a physical time scale. In auto time scale, you can choose the length scale to be conservative, which is slower but more robust, or you can choose it to be aggressive, which is faster but could lead to stability issues if in certain cases. So I'm going to keep this as default values. I can also set my convergence criteria. I usually set my convergence criteria to be a little bit lower. I'm going to change it by order of magnitude over here. Again, this is problem dependent. The reason for that is that in certain cases, the residual values might converge faster before the global quantities, such as if you're monitoring the mass flow rate, or in this case, the pressure drop. It might not have converged while the residual quantities might have converged. So you actually didn't reach a steady state. So I lower it a little bit more to make sure my global quantities have converged. I'm going to set this to OK. So like I mentioned, I want to also monitor some of the global quantities. In this case, I'm going to define the pressure drop. So I can define an expression for that. I call it P drop, which is essentially the area average pressure at the inlet minus the area average pressure at the outlet. So the difference of the two is defined as an expression. And I go to Output Control to the Monitor tab, and I can monitor a point on an expression over here. So I call it I'm monitoring an expression for P drop. So by doing so, I'm looking at the value for P drop at every time step, and then this way I can make sure whether or not my pressure drop has converged. So once I set that, I can go to this solver, run it in serial or parallel as I want. And when I look at open the solver manager, if I look at the residue values, I can see that my mass and momentum values have converged to the desired convergence criteria. So if I look at the user points, it gives me the pressure drop variation in time, in pseudo time. And you can see that the pressure drop reaches a steady state value in this case, so I know that my solution has converged. All right, so we are done running the solver. Now we take a look at the results, and we do that by opening up the results box, which opens the results in the CFD post. So this is how it looks like. So we're going to look at the quantities of interest to make sure it follows the physics that we're expecting it to do. So in this case, we're going to look at both the pressure and the velocity. So to look at the pressure, what I do is first take a section through the flow domain, create a plane, and in this plane, I can plot the pressure values. So I plot the pressure values. So you look at it, and you can see that at the outlet, the pressure is, you're looking at the relative pressure. So outlet, the pressure is 0, and at the inlet, you have a higher pressure. So as the flow enters the valve region, you see a pressure drop, and as it exits, again, there's a pressure increase. This happens because the fluid, as it enters the valve region, due to a smaller area, it speeds up. And with a faster flow, the pressure drops, and as it exits, due to, again, the area change, now the area is increased, the fluid will, again, deaccelerate. And in the process, the pressure is recovered. So does it follow physics? Yes, you can take a look at the flow velocity, and you can see this is exactly what happens. The flow is actually accelerating in the valve region. As it is exiting, it's deaccelerating. Another thing to notice over here is that as the flow exits, you can see that there is a low velocity region at the top and the bottom of the pipe. Now, this is the region which corresponds to a small recirculation region which we are expecting to see due to the sudden expansion. So we can look at it by we can find out whether or not it's true by looking at the streamlines, and you can see as I plot the streamlines, I indeed have two recirculation zones in this section, so which means that the flow is separating in this region. Now, if you remember, I mentioned something about having a well-posed boundary condition. Now, what would have happened if I placed my outlet boundary to be over here? Because I'm only interested in seeing the flow through the valve region. In this case, you will run into trouble. So let's look at that scenario. So I'm going to bring up the slide. So this is the scenario we're encountering right now. The flow exits, the flow separates, and there's a small recirculation zone at the top and the bottom. Now, if I place my boundary condition over here as the outlet boundary only allows for the flow to go out, not to come back in. And in this case, what will happen is that it will place a wall in these regions to make sure that the flow does not come back in. So you'll end up with a wrong solution, essentially. So this is not the right boundary condition to use. What you should do is, like we had done for this particular case, you can extend the flow domain out, if it's possible, to make sure that you have placing the outlet boundary far away from this recirculation zone so that it won't affect the flow pattern. This is the right condition to use. However, in certain cases, it might also be possible that you cannot place a faraway boundary like that. So in this case, you are better off using an opening boundary condition, which does allow for a recirculation zone and allows some of the flow to come back in. Right, so what we examined so far is we have done a qualitative comparison of the pressure and the velocity for the base case, which is the fully open case. We want to also do some quantitative analysis. For that, we can look at the numbers such as the pressure drop in the across the valve. But before we do that, I want to compare this case with another one, another scenario where I'm modifying the geometry and making it partially closed. In this case, I'm again redoing the geometry, recreating the mesh, and then I'm linking it to a CFX system. I have exactly the same setup, the same inlet condition, and when I finish running the simulation, I can compare this using the results component system. I can link both the fully open, the partially closed cases, and if I open this in CFD post, what it does for me is it syncs up the view between the two results. So this is the fully open case and the partially closed case. So when I rotate, I can see and more of an apple-to-apple comparison between the two cases. So is also the case when I'm also plotting the variable values such as pressure or velocity. So let's take a look at that. If I plot the contour for pressure like I've done previously, same way looking at a cross-section, the same contour levels, and this gives me a comparison between the two cases. So what we notice over here is at the inlet of the partially closed case, we have a higher pressure as compared to the fully open case. Note that the exit pressures are the same. However, the inlet pressure is higher for the partially closed case. Now, what it implies is due to the change in the cross-sectional area, you require a higher pressure drop is required in order to drive the same amount of flow for the partially closed case as compared to the fully open case. Another thing to notice is that you have a higher pressure drop. The pressure values are lower for the partial drop case, partial closed case at the exit of the valve. If you look at the velocity, you can notice that as the flow enters, it accelerates much faster. There's an acceleration faster than the fully open case, and the flow is deflected, and as it exits, so it creates a different flow pattern for the partially closed case as compared to the fully open case. Notice that the flow is deflected towards the top. So if I plot the streamlines, you'll note that towards the bottom I have a higher recirculation zone, and also there's a loss of symmetry in this case as compared to the previous base case we tested. All right, so this is the qualitative comparison. Now let's take a look at some of the quantitative comparison we can do. So if we go to expressions, you will see that I have a P drop, which was the expression I monitored during the run. But this gives me the pressure drop from the inlet to the outlet. I also want to look at the pressure drop across the valve region only. So what I can do is I can define two additional planes corresponding to the inlet and the outlet, plane 2 and plane 3, and I can measure the pressure drop across it. So I'm going to define a new expression called P drop valve, and I'm going to calculate the average pressure at plane 2 minus the average pressure at plane 3. So if I evaluate this expression for the case 1, which is a fully open case, you can see the pressure drop is approximately around 0.9 psi, and for the partially closed case, this pressure drop is around 3.8. So nearly four times increase in pressure drop is seen for the partially closed case. In addition to this, CFD post has also some inbuilt functions which can be used to calculate additional quantities such as area, or in this case, I'm also interested in looking how much is the pressure force on the walls of the valve. So I'm going to choose a function called force. The location for that is the region of the wall on the valve, and I'm going to examine all the cases. Once I do that, I get an integral quantity for force, which is 0.3 for the fully open case and 1.4 for the partially closed case. Again, you see almost a 4 times increase in the pressure force. So using CFD post, you can do both quantitative and qualitative analysis. So the case we examined just right now is the change to the geometry for the same flow inlet flow. How about a case where we keep the same geometry but increase the inflow rate? How does the pressure drop change with that? So for this, I'm going to choose the partially closed case. So I'm going to set up a case where I'm doubling up the inlet condition. So the inflow is at a higher speed as compared to the the base case. And I'm going to compare the results again over here. So the setup is mostly the same except for the inlet condition. And when I open the results, it will bring up the comparison between the two cases. And here I want to point out another great feature of a CFD post. It's called case comparison. Now in case comparison, if we make the case comparison active, it will compare two cases. In this case, I'm comparing the higher flow rate versus the lower flow rate. And when I do apply, it will not only synchronize the views, but it also will give me the quantitative difference between the two cases for any variable. For example, if I plot the contours for pressure, you will see, as expected, with a higher flow rate, you also have a higher pressure drop. And you're looking at the same contour values over here. But in the third view, I can get the difference between these two. So how much is difference at the inlet pressure? If you look at these values, it's approximately around 9.4 psi. So this way, I can calculate the exact difference between the two, and I can also zoom in at different locations and compare how much is the difference in the values over there. Similarly, if I look at the velocity, I can also examine how much higher velocities are obtained in the valve region compared to the base case. So I'm getting nearly 7 meters per second higher velocity for the higher flow rate as compared to the base case. Right. So similarly, you can also examine the expressions. So let me bring up my slides and look at the results we have found so far. So we have done a comparison of the fully open case and the partially closed case. This is the difference in the geometries, and you can see that the pressure drop increases nearly twice for the partially closed case due to the increased resistance to the flow. So is also the case of the fluid force on the wall. You have nearly a 4 times increase with that. If you examine the different flow rates, you get something similar. With a doubling up of, by increasing the flow rate nearly twice, I also get a 4 times increase in the pressure drop and nearly a 4 times increase in the fluid force on the wall. Notice in this case what I'm doing is that when I'm creating new component systems in Workbench, I'm comparing a parameter which is the inflow rate over here between the two cases, and if I wanted to do a parametric study, so for example for 10 different parameters, this will be cumbersome just doing this way. But Workbench has a great feature called usage of design points, and it's very useful for conducting parametric studies. How it is done is by defining some kind of an input parameter. In this case, I'm defining the inlet velocity, for example, and the corresponding output parameter, P drop, in this case. And I can define different design points. In this case, I can increase it to 2.5, 3.5. I can use the design point feature in order to evaluate all these results, and I can get a table like this. Now, the details of this kind of a parameter study will be covered in one of our future e-learning sessions, where we'll talk about the ANSYS Remote Solve Manager. Okay, one more thing before I wrap up my webinar. Consider a case where there are certain cases where cavitation occurs in the flow. So consider the case where I'm just picking up a hypothetical scenario where the valve is not fully closed. Instead, I've rotated to such an extent where the flow coming in is exiting with a very high speed. And in this case, the pressure in some of the regions in the flow could very well drop to a pressure which is well below the saturation pressure. In this case, what will happen is that the water will cavitate. So in this, you can see this is just a hypothetical scenario where you can see that the pressure is well below the saturation pressure, causing the water to cavitate. And here, you can no longer consider water as a single-phase fluid. You have to make sure that you have the cavitation model included in your calculations, and that will give you the correct physics. So that's it for today's webinar. In summary of what we've done so far, I've given you an overview of a typical flow-through valve, We looked at the geometry and the meshing requirements, and I walked through how you can set the solver settings for this particular problem using the ANSYS CFX. And finally, we used CFD post in order to analyze and compare the results. Here we can do both qualitative and quantitative comparisons.